Alright, this is one of the examples that we worked in class. The question is, we would like to find the Thevenin equivalent seen between these two nodes. So we would like to replace this whole circuit by its Thevenin equivalent. As we discussed in class, we can find the open circuit voltage in this circuit. That would be our VT, Thevenin voltage. Then we short these two terminals out, find the short circuit current, and that would be our IN. Once we did that, our RT will be V open circuit over I short circuit. And that's one way to complete this example. The other method that I discussed or briefly mentioned in class and never really showed an example was that we can attach a source across these two terminals, the source V and with current I. So these are parametric current and voltage. So based on these two, we would like to find an equation like V equals R Thevenin I plus V Thevenin. So we can analyze this circuit to find such an equation. Once you find this equation for this circuit, these two, you will have two numbers here. This number, which is the coefficient of I, would be your Thevenin resistor, and this constant here would be your Thevenin voltage. So in this example, I would like to show that I would like to solve this circuit using this technique. So we attach a voltage source with the voltage V parametric and try to find its current based on the circuit. The current is also parametric, the current is I. Based on this, we find an equation like this, and I can get the Thevenin resistance and Thevenin voltage. So how can I apply this technique to this circuit here? So I noticed that I can use node voltage analysis in this circuit here. I can label these nodes. If I assume this is my ground, this is VA, this is VB, and this node, what is the voltage of this node? If you follow this line, it would be the same voltage as V. Alright, the next step is to see if there is any known voltages here. So there is one known voltage here, VA. Obviously VA is 40 volts because the 40 volt voltage source is connected between my ground and this node. So VA is 40, it's known. VB is unknown, and the voltage of this node is parametrically known as V. Alright, so the first thing I do, I can write a KCL for this node. So I can assume these three current directions and write the KCL at this node, node B. What is that KCL? This current going out, 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 so some of them should be zero. This current going to the left, VB minus VA, VB minus VA, which is 40 over 60, plus the current going down, VB over 80, 180, and the current going to the left, to the right, is VB minus V divided by 15 equals 0. So before going any further, I would like to get rid of these denominators here. So what I can do is if I multiply both sides of the equation by 180, then I will get rid of these, will be removed. These denominators will go away and I will have a simpler equation to work with. So in the first term here, 180 over 60 is 3 VB minus 3 times 40 plus the second term, 180 and 180 cancel, so it's just VB. The third term, 180 divided by 15 is 12, so 12 VB minus 12 V equals 0. So I can further simplify this equation. 3 VB here, 1 VB here, and 12 VB is 16 VB minus 12 V, and the only remaining term is this 120 here. Alright, now I have one equation. So what is my end goal? My end goal is to have an equation like this: V equals RTI plus VT. So in this equation I have an extra VB. I have V, which is good. I need a V in this equation, but I need to remove this VB and have I instead. So I need an equation to relate VB to I. So if you look at the circuit, I notice that I can write a KCL for this node here. This current is entering, I enters, and 2 amps leaves the node. So the current entering this node from VB to V, the current going to the right, is VB minus V over 15. This current entering is I, and 2 amps leaves. So from this equation I can deduce that my VB will be 2 minus I going to the other side times 15, so 30 minus 15I plus V. So VB equals this. So once I plug this in this equation, I will only have terms, I will only have V and I in the equations, and the VB will be eliminated. So let's do that. So I use this in here, and the result is 16 times VB, which is 30, minus 15 I plus V minus 12 V equals 120. So I can further simplify this. Number one, I can divide everything in this equation by 4 to make it simpler. So I divide this by 4, I divide this by 4, I divide this by 4, and I will have 16 by 4 is 4, so 4 times 30 is 120, minus 4 times 15I plus 4V minus 12 over 4 is 3, 120 over 4 is 30. So if I further simplify this, 4V minus 3V is V, and I move this to the right hand side, so it will be minus 90, and 60I to the right hand side is 60I. Alright, now I compared this equation with this. Let me copy it here. So if I compare these two equations, I have two parametric equations. V equals something times I plus something else. So this would be my RT and this would be my VT. So my RT is 60 ohms and my VT will be minus 90 volts. So the Thevenin equivalent will be a voltage source in series with a resistor, which is 60 ohm in this case. So the voltage source we typically have plus minus like this, and the voltage, but here the voltage is minus 90. So what we can do, we can flip these polarities and put 90 volts here. That would be your Thevenin equivalent of this circuit, which agrees with what we did in class. So the other thing that I would like to briefly discuss in this video is this. Let me just copy this circuit again down there. So here's my circuit. The objective was to find the Thevenin equivalent of this circuit. Let's get rid of this extra stuff here, okay? So the Thevenin equivalent involves finding VT and RT. I would like to show a way that we can find RT in a much simpler way. So in order to find an RT in a circuit like this, what we can do is to find RT directly. We turn off all independent sources. Once we do that, then we can look at the circuit and find the Thevenin equivalent. So there are two independent sources in this circuit. There's a current source and a voltage source. So the first thing I do is I turn them off. What do I mean by turning off? Turning off a voltage source means I replace it by a short circuit. Turning off a current source is replacing it by an open circuit, or just deleting this current source. So now that I have turned off all the sources, my Thevenin resistance is basically the equivalent of this network here, which is what? Which is 60 in parallel with 180 and the whole thing in series with 15. 60 and 180, if you do the math, is 60 times 180 over 60 plus 180. Here we get 45. 45 plus 15 is 60. So I could easily, in a simple step, find the Thevenin equivalent here. The Thevenin resistance is this, 60 ohms. And if you go back here using the other method, it's also 60 ohms. So the results agree. Now I need to find the Thevenin voltage. I can find it, for example, the open circuit voltage here, and that completes the analysis. So just to recap, in this video I tried to use this approach of finding a Thevenin of a circuit. We apply or attach this voltage source V, and just be careful about this voltage polarity and this current direction. We will try, based on this circuit, we try to find the relationship between V and I, something like this. So it's a parametric equation. Once we find that, then the coefficient of I would be my R Thevenin, and this constant here will be my V Thevenin. So I did node voltage analysis for this circuit and eventually got this equation. When I compare it with this original equation, my R Thevenin is 60 and my V Thevenin is minus 90. So the Thevenin equivalent is this. I also explained that there is a way to directly find the Thevenin resistance, which what you do is you turn off all the independent sources first. So this is the same circuit with sources turned off, voltage source shorted out, and the current source open circuit, or just we deleted the current source. And now we try to find the equivalent resistance in between these two terminals, which is obviously 60 in parallel with 180, is the whole thing in series with 15, and we get 60 ohm, which agrees with what we did here. Alright, I hope this video has been